All right. Are we ready? Okay, good, cool. All right, good morning. So this has been really fun. Every day is like going to the beach, to the Hollywood and so forth. But there's a price to pay, it turns out. And the price to pay is to have to give 2 talks. I've never attended a program in which I have to give 2 talks. And also there was some confusion because the organizer asked me to give a tutorial and a research talk. Now, I could never figure out what is a tutorial and what's a research talk. So the solution is to give a semi-tutorial, which is a convex combination of a tutorial and a research talk. So I'm going to talk about basically the first half of the lecture will be a tutorial on a concept called maximal correlation, which was invented 70 years ago. If you heard my first talk last week, you may think that this guy's really old. He's always talking about things that are 70, 80 years ago. But it is true, it is true. And then I'm going to connect it to PCA. So this is joint work. In fact, he did most of the work, actually. Joint work means he did most of the work. So hey, Faizi. And he's a postdoc in our group. And in case you're looking for faculty next year, he'll be on the job market, okay? So please recognize him. It's very happy. All right. Okay, so here are the 3 questions I want to address in this tutorial, semi-tutorial. One is, if you have 2 random variables, what's a natural definition of dependency? And 2 is, if you have more than 2 variables, say p variables, how do you define dependency? And 3 is, what is the connection to PCA? Now, these questions are pretty broad statistics questions or data science questions. It used to be called statistics question. Now it's called data science question. You may think, what's the connection to the bioinformatics program? Well, you know, in bioinformatics, PCA is a very general tool. And so I want to serve 2 purposes, which is 1, to sort of give a tutorial on these basic data science concepts, and 2 is to make a bit of connection to bioinformatics at the end, where I talk about a few applications, okay? But these concepts are pretty general. All right, so we start from probability 101. Okay? Probability 101 means back to 1895. So this guy is called Pearson, and he asked this question, well, how do you define dependency between 2 random variables? So he came up with this concept, which we all know from probability and statistics 101, which is if you have 2 random variables, x1, x2, then the Pearson correlation is the expectation of the product of x1, x2 centered and normalized by the variance, okay? So how many people have not seen this concept? Good. Someone's putting up his hand. This is a little bit concerning. All right. Hopefully it's not a UCLA student. All right. All right. So this is Pearson correlation. We all know this concept from basic probability and statistics. And this is a very long history. So let's look at the basic properties of this Pearson correlation to see the strengths and weaknesses of this measure of dependency. So first is normalized. So it's between +1 and -1. So that's a good thing, because that means you can compare correlation between different random variables. You're normalized, and it's a reasonable concept. 2, if the variables are independent, then it's 0. So that's a sensible thing, right? 0 means no correlation, independence. However, there is a drawback that we learned from basic probability, which is even if the variables are dependent, it can be 0. Okay, so this is something we learned in basic probability. That is, this measure of dependency is not the same as independence, which is a bit of a drawback because independence is like a fundamental notion. Okay. However, if we restrict to jointly Gaussian random variables, then it is true that there's 0 if and only if the variables are independent. Okay. So that means for jointly Gaussian random variables, Pearson correlation is in some sense equivalent to independence in the sense of whether 0 or non-0. So that's a good thing for jointly Gaussian, but not true in general. Here's another limitation, is that even if one variable is a function of the other, it's not necessarily +1 or -1. So the extreme is not necessarily measured full correlation. Is another drawback. And the fifth drawback is that it is a label variant. Now, what does it mean by label variant? So imagine if the random variables are discrete, okay, categorical. Then this quantity depends on how I assign numeric values to those categories, right? Because you can see the expressions in terms of x1, x2. So if I assign certain numerical values, I get a certain value. Another set of numerical values, another value. So therefore, it's not a very natural measure of dependency for discrete random variables particularly. In general, it's label variant. That is, how you label the random variables will affect the value. So that's a drawback, okay? All right, so there's so many drawbacks that people start thinking about, well, how do you remove some of these drawbacks? Okay? And just to give an example.
Sorry, David, just to clarify.
Yes.
For this label issue, if it's like Bernoulli only takes on two values,
yes.
and you label one, the other 0.
Yes.
It's invariant if you switch, just changes the sign.
Yes.
Right? So what's an example of a?
So for two values, it's okay because you center around the mean, right? You center around the mean. But if you have 3 or 4 values, then it starts making a difference. Because now, for example, if you assign random variable 0, 1, 2, 3, 4, this is different from 0.5, 1.5, if it's a nonlinear change in the scale, right? So then it's dependent, okay?
So
good.
Once it's ordered, you already have this problem, right? It doesn't even have to be categorical.
Yeah, in general. I mean, this is true in general. Yes, exactly. It's real value, so you can map it to any monotonic function, and this value will change. But in particular, it's sort of more noticeable when you have discrete random variables, because then the real value doesn't really have any sense. So it depends on how you label them now.
For ordered as well, the real value doesn't sense.
Right, okay, fine. Yeah, that's true. Good, all right. So really what's happening here is that Pearson correlation is in some sense a measure of dependency under linear transformation. So that's why in some sense for jointly Gaussian is 0. You've been only variables independent because for jointly Gaussian, linear transformation is sort of a natural transformation. So just to see this picture more clearly, so here's a bunch of points which have kind of a roughly linear relationship. And you can see that the correlation is very close to 1, which is intuitive in this picture. But if you have 2 random variables which have this kind of a bit of a nonlinear relationship, then the correlation could be small, which you would think that there's very little dependency, but actually there's a very strong nonlinear dependency. So it's not capturing that. Okay? So then around the Second World War time, a bunch of people thought maybe there's a way to sort of extend this. How do you extend this? How do you sort of avoid all this limitation of Pearson correlation? And then they came up with this notion called maximal correlation, which I'd like to spend a little bit of time describing. Okay? So what they're saying is that let's focus on the label invariant issue, right? So since the correlation is label variant, then you can think of phi I as some function which is a relabeling of x1, x2, right? And now instead of computing the correlation between x1 and x2 directly, you compute the correlation between phi of x1 and phi 2 of x2. Okay? Now obviously this quantity depends on phi 1 and phi 2, right? So that's not good because you want something which is intrinsically dependent only on the joint distribution between x1 and x2. So what should we do? Well, the proposal is to find the phi 1 and phi 2 that maximizes the Pearson correlation after relabeling. So in other words, we should not assume a particular labeling, but we should find the correlation that maximizes over all possible labeling. The labeling constraint being is centered and unit variance, so it's normalized. Okay? So you can see from this definition that in the case of Pearson correlation, this corresponds to phi 1 and phi 2 being linear function. And since it's centered and unit variance, there's only one such linear function. In general, you should allow a nonlinear function, and this is the definition of maximal correlation. So how many people here have heard of this concept, maximum correlation? Oh, wow, okay, relatively few. Okay, well, yeah, it's kind of strange. When we came across this concept, we thought it should be very popular, but actually very few people learn about it. So part of this tutorial is to sort of promote this concept more for these people. Okay, all right. So this is maximum correlation. Now let's study the property again. Just like Pearson correlation, it's between +1 and -1. This is Cauchy-Schwarz, basically. Now, in this case, one can show, that René showed actually, that if the variables are independent, then it's 0. And it's if and only if now. So the independence and the dependency measure is now consistent. 3 is that if the variables are jointly Gaussian, then it reduces to Pearson correlation. So in other words, the optimal phi1, phi2 here, if the variables are jointly Gaussian, is linear. So this is good. Because in some sense, Pearson correlation is already the right measure for jointly Gaussian random variables. That was what showed earlier. This says that even if I define a more general notion, we still fall back to the Pearson correlation. So it's consistent with the Pearson correlation. And 4, if one variable is a function of the other, then it's +1 or -1. And 5, very important point. Now it's label invariant, because I can take a supremum over all labeling, and therefore, however you relabel x1, x2, it just sort of get cancelled in the optimization anyway. So it's label invariant. So there are a bunch of very nice property, and I think this is a pretty good measure of dependency. Now, you may think, though, that while Pearson correlation is just a direct computation of the expectation, this involves a complicated optimization, a maximization over phi1, phi2. Then if x1 and x2 takes on, say, large number of values or even real value, the optimization may become cumbersome and therefore lead to a bad measure in terms of computation. However, it turns out that this is not the case. For example, if you have 2 discrete random variables, x1, x2, categorical random variables, then it turns out that you can compute the maximum correlation using a very simple computation. And this was shown by Witzenhausen in 1975. So what he said is that let's define a matrix Q, which is the joint distribution between x1 and x2, normalized by the square root of the 2 numbers. Okay? So suppose the random variables x1 takes on, say, 5 values, x2 takes on another 5 values. Then this is a 5 by 5 matrix, where the entries corresponds to the joint distribution, but normalized by the square root of the marginal. Okay? A pretty straightforward computation, which I will not do here due to lack of time, but you can do following Leo's tutorial. Then you should do a homework, but I won't ask you to do the homework real time. You can do it at your leisure afterwards. When is it due? At the end of the program, of course. At the end of the program. Okay. And it turns out that the maximum correlation is equal to the second largest singular value of this matrix. Okay. So you may think that computation of this maximum correlation may be complicated, but it turns out it's just a singular value computation. Okay. And this is relatively easy computation to compute the second largest singular value matrix. And once you compute this, then using left and right singular vectors of this matrix correspond to this value, then you can compute also the optimal transformation. So underlying this maximum correlation, there's also a relatively easy computation. Okay? All right. So just to give an example, since it's a semi-tutorial. So here we have 2 random variables. Say x1 is a gender variable, and x2 is a disease variable. And 1 and 2 corresponds to male and female. 1, 2, 3 corresponds to healthy, benign cancer, malignant cancer. So if you do a correlation analysis or Pearson correlation analysis, then you write out the joint distribution which in this case is between the random variables x1 here and x2 in the columns and x1 in the rows. 6 numbers, which describes, of course, in practice, you collect this data from empirical data, but you get a joint distribution. And the Pearson correlation says is a small number, close to 0, 0.06, okay, minus 0.06. And just to emphasize this, the correlation value depends on the label, how you label these values, okay? So this label is now 1, 2, 3, and 1 and 2. Maximum correlation allows you to optimize over all possible labels. And if you compute that Q matrix that I wrote down earlier, you get this matrix. And when you compute the second single value of this, you get this number, 0.7, which now suggests that you have strong dependency, relatively strong dependency. And then you can also compute the optimal variable transformation. So now it's saying that the labeling between of 1 and 2 should be changed to -1 and 1, and this should be changed to -0.5, 1.1, and -0.95. So the labeling does not have to be integers. It can be any real number. Okay? So this is a worked out example. All right. Okay. So this brings me to the second half of the tutorial, semi-tutorial. Okay. So, Hey and I were discussing this, actually even before he joined our group. And we said, well, you know, there's something strange about this thing. Is that there's no activity on this problem since 1959. 1959 is a long time ago, isn't it? Like 60 years ago. How come nobody did any more work on this? In particular, there's a very natural question. The natural question is, well, we've defined maximum correlation for 2 variables, right? That's what these 3 folks defined. I can't really pronounce the name, so I just call them 3 folks. Actually, we can call this HGR correlation because these are the initials of these 3 people's name. Now, it's for 2 variables, right? What about for 3 variables? You know, in data science, we deal with many variables. We don't deal with 2 variables, right? We have many features, for example, 1,000 features, 10,000 features, 20,000 features, 20,000 genes. So what's going on? What about for more than 2 variables? Strange. But no one has asked this question even. And so we did. Last year we did ask this question. And we came up with an answer, which I think is pretty interesting. So I would like to share with you here. Okay? So recap, we have maximum correlation, which is a generalization of Pearson correlation for 2 variables. And now we're asking, what is a natural generalization when you have more than 2 variables? Okay, so let us try to, since it's a semi-tutorial, let's try to seek the answer ourselves by drawing an analogy. So we have bivariate, which means 2 variable, and now I want to generalize to multivariate, which is more than 2 variable, and I want a natural dependency measure. So in the bivariate case, I have 2 variables, x1, x2. Let us club it together and call it a random vector x. Okay? So boldface means vector. Thank you. Notation is very important for me. So boldface means vector. Now we have n variables. We have p variables. So I'm using statistics notation here. P is the number of features. Okay? x1 up to xp. Okay? Good. In the case of 2 variables, Pearson correlation, which is the basis of maximum correlation, because I'm generalizing Pearson correlation to maximum correlation, is expectation of x1, x2. I'm lazy here now. I'm just assuming these guys are already 0 mean and variance 1, so I don't want to bother subtracting the mean and dividing by the standard deviation. I get a number. And then I'm going to generalize it by taking maximum of rho, the function, right? So now I want to find a generalization of the maximum correlation. To do that, I need a generalization of this number to n variables. OK, now this is still at the level of probability, basic probability. Now I need to ask you guys, This is a very important question. What is a natural generalization from 2-dimension to p-dimension of this number? What is the analog of this number for a p-dimensional random vector? I wish I have a blackboard. So it turns out that behind the screen is another screen. I guess UCLA has gone beyond the days of blackboard. There are no more blackboards anymore. Okay, so what is the natural generalization of the Pearson correlation to p-dimension? Expectation of the product of all the variables. Yes, very good. Now, how many numbers are there? No. Expectation of product of all variables is not just p numbers. How many numbers are there? Well, you have p variables, and you take the product of each one of them with another one. There are actually p choose 2 numbers, right? Because any pair of random variables, you can multiply them and take the expectation. So here we have one number, and here we have p choose 2 numbers. Okay? Now, the p choose 2 numbers are just a bunch of numbers, right? But in probability of statistics, we never look at those p choose 2 numbers as a bunch of numbers. We organize them in a certain way. How do we organize them? Correlation matrix, or the covariance matrix, right? Right? So that's the object. This object is the covariance matrix, which is the expectation of XX transpose. XX transpose contain all the product, as was mentioned, of xi times xj, but organized in a nice matrix form. So this is a great advance, from in statistics, which is instead of thinking a bunch of numbers, think of it as a matrix. This seems like trivial, but it's a really important thing, because matrix by itself is an object. And now you can talk about various property of this matrix. So that's very important. So you may think, why is this 2 variables have only a single number, whereas p variables have many numbers? In fact, you can also think of this as a matrix, because 2 variables have a 2 by 2 covariance matrix. Now I've normalized the variance to be 1 already. So the diagonal elements is 1, 1, so it does not contain any information anymore. So this is just the off-diagonal elements, which is 1 number. It's symmetric. So I have 1 number, and now I have a whole matrix. Okay? Now, yes?
There's 2 other notions that maybe are sort of more modern, but maybe natural to consider. One is the inverse of this matrix, which is the precision matrix.
Yes.
Which is probably, some people argue, more natural way to think about independence.
Yes.
Conditional independence. And the other one is maybe do not p choose 2 but 2 to the p numbers, which are all the products. That's something that second one I don't know if people have been thinking about. But,
oh, you're now taking product of x1 times x2 times x3, etc.
Yeah, all
Right. Then you get to more complicated situation. In fact, part of the role of this talk is to actually maybe get people thinking about this problem. So far, we're focused on only the covariance matrix, which in some sense cover the inverse case, because next we're going to talk about this, any function of the covariance matrix can be in consideration. So let's focus on that case first. So now what do? To generalize from this to maximum correlation, okay, we take a supremum maximization over all function phi1, phi2. Now what does that mean? Well, let me draw a picture here. So let's say this is the real line, okay? And now what I'm trying to say is that if I pick a particular phi1, phi2, I get a point on this real line. And I want to pick one for which this number is the largest, so on the right extreme of this area. Okay? So this is a very cumbersome way of thinking about this optimization, right? But this leads to a natural generalization for p variables. Because now I can think of this line is no longer a line, but now I can look at the space of all covariance matrix. So in other words, I take a function of x, which is component y. So this is a nonlinear function of x1, nonlinear function of x2, nonlinear function of xp. For each choice of this function phi, which is a vector function, I get a covariance matrix. This is the original one, which may not be the one I want. As I vary over all possible phi, I get a whole region. Just like when I vary over all phi1, phi2, I get a whole line. But now, because I'm dealing with a high-dimensional object, I don't have a line anymore. I have a very high-dimensional space. In fact, this is space dimensional p times p, or right, roughly p squared dimension. Actually, not exactly, but p choose 2 dimension because of the symmetric constraint. Okay? So now I have a problem. Because now I don't know how to define this maximum correlation anymore, because here I have a single number, right? So the maximum value is a natural choice of optimal phi1, phi2, and I use that number to define maximum correlation. But here I have a set. So what I need is some scalar measure in order to choose the right phi to optimize. So I need something to optimize over. Okay? And so here I have a space. The question is, what is a good optimization criteria? OK, let's go for an example. So suppose I have 2 matrices in the set. One looks like this, and one looks like this. These are 2 possible covariance matrices, maybe by applying 2 different functions on the original random variables. Now, obviously, I cannot compare them because this is, 1, 2, 3, 3 numbers here, another 3 numbers here is not ordered. I don't know how to order them. But remember, the goal here is to capture dependency, right? So I want to say somehow that maybe one matrix is more dependent than the other matrix. So what is a natural measure of dependency? Well, if I have 3 random variables, then the more dependent of 3 random variables would mean what? Well, what is the right quantity to look at? The determinant is one possibility, yes. But actually, determinant is not the most basic quantity to look at, though.
The total of the min or the max?
Yes, the min and the max of what? The eigenvalues. So the key quantity to look at are the eigenvalues. Right? So determinant or the min and the max are all function of these eigenvalues. So let us look at the more basic thing, which is the eigenvalues themselves first. So look at this set of eigenvalues and this set of eigenvalues. Now this one has one eigenvalue or singular eigenvalue of k1, which is very large, and the other ones are very small. So that means this matrix is close to rank 1, not exactly rank 1, but close to rank 1. So if you look at the joint distribution of random variables, then they lie very close to a one-dimensional subspace. So this should be higher dependency than this dependency, right? OK? So therefore, a natural criteria is to choose the covariance matrix in this set of all possible covariance matrices under applying nonlinear transformation to maximize the sum of the largest Q eigenvalues of the covariance matrix. Okay, so this is so-called Q-fan norm of the matrix K. Okay? Now Q is a parameter in this optimization. Okay, so it could be that for different Q you get a different optimizing K. But nevertheless, it is a reasonable optimization criteria. Because what I want to do is to choose the transformation to make this covariance matrix as low rank as possible. I want to push all the energy as much as I can into a few low-dimensional subspace, a few dimension. Yes?
Is it right to interpret this as actually wanting to minimize the rank and you're relaxing? And that's why it's considering.
Yeah, so minimizing the rank is sometimes not possible. right? So the minimum rank could be the full rank, right? So that is not a very interesting problem, because it could be that whatever transformation you get, you can't really collapse the rank, right? However, minimizing this or maximizing the sum, or in other words, minimizing the sum of the residual eigenvalues beyond a certain Q dimension is equivalent to, similar to, sort of the effective rank being small. Yes?
Why do you have to stop at Q, not do the nuclear norm, which is an approximation of the rank?
Sure, you can have many other. So first of all, there are many such metric. We're not claiming this is the only one. However, there's an interesting connection of this to the PCA story. So that's one reason why we chose this one. Yes. Yes.
You could get the same sum by having an hyperrank 1 matrix and having a matrix that's like spherical in 3 dimensions.
Okay.
Choose Q to be 3. So do you want to distinguish those cases where, like, let's say like you have like 3 eigenvalues that are all like 1 on 1, or 3, 0, 0.
Yes.
Do you want to distinguish those?
Yes, I want to choose 3, 0, 0. So there's some. So because I normalized the diagonal elements to be 1, okay? So the sum of the eigenvalues must be the same, no matter what phi I choose. The sum of the eigenvalues is always equal to 3, because the sum of the diagonal is equal to the sum of the trace of the matrix, the sum of the eigenvalues. So this one, the question is how do you spread the energy across these 3 eigenvalues? And I want to choose the one. If Q equals 1, I want to choose the one in which the largest eigenvalue is the biggest among all possible transformation. Yes?
I think, David, the question, go forward a slide. It's a question that you're taking the sum over the lambda, so whether it's 1, 1, 1 or 3, 0, 0 would be the same.
But this is Q. If Q equals 3, it's not a meaningful problem. Because if your dimension is 3, and you choose Q equals to 3, this optimization is always equal to the same number, 3.
So you have to choose Q.
Yes. So I emphasize that Q is a parameter in this optimization problem. In some sense, this is a family of optimization problem. Yes. Sorry?
Why don't you square the eigenvalue?
Why don't I square the eigenvalue? Yes.
Hey, I want to remind people we have a coffee break immediately.
But it's a good thing. It's a good thing. Yes. So again, so that's why I want to draw this picture first, is that the fundamental object is this object. What performance measure you want to optimize over is a little bit less fundamental, perhaps. But I'm choosing a particular one. And this particular one, I can draw a nice connection with PCA. Okay? But you can come up with another one that you like better. And that's fine. I have no objection to that. But so this is called, we'll call this maximum correlated PCA. And the question is, why this name? Why this name? So PCA, I remind you, is the following. I take P variables, and then I do a low-dimensional projection, linear projection V, into, say, Q dimension, where Q is what you choose. You want to do PCA of dimension 2, as John likes to do, or Q equals to 50, or Q equals to 30. Q is what you choose, right, in the PC analysis. That's a parameter in your PC analysis. All right? You choose that dimension, you get V. And one interpretation of PCA, which I like to use here to connect it to MCPCA, maximum correlated PCA, is that in effect what you're doing is you're choosing V to maximize the sum of the variances of the transform variable. Okay? So PCA can be interpreted as choosing the best low dimensional embedding to capture as much variance as possible. Okay? In other words, you lose, hopefully, as little information as possible. So in this picture, now you can think of the MCPCA pipeline as follows. I have a bunch of input variables, the features. And now I allow you to choose phi1 up to phi p nonlinear, possibly nonlinear transformations, and then you project to Q dimension. And you can show that the criteria of maximizing the sum of the eigenvalue of the covariance matrix is equivalent to maximizing again the sum of the explained variance. But the maximization is not only over V as in PCA, but also over phi, the nonlinear transformation. Okay? So therefore, I view this particular objective I chose as a natural generalization of PCA, because now you're maximizing over phi and V, the nonlinear function of the coordinates, the features, together with the transformation. So here's the commutative diagram, as the algebra people would call it. So I start with two variables, Pearson correlation. If I consider nonlinear transformation, I get two variables, maximum correlation. This is due to HGR in the mid-1900s. If I go downwards here and I keep the linear transformation, but I extend from two variables to p variables, I get PCA. So PCA is a natural generalization of Pearson correlation because they all deal with the covariance matrix. Okay? Now, if I want to move this way, then I would like to allow nonlinear transformation, and I would like to extend two variables to p variables, and I get p variables maximum correlated PC, which is MCPC. So this is the natural diagram connecting all these concepts. Okay? All right. So I won't do much math here, but we do have a theorem that we're pretty proud of, so I would like to quickly mention it before I go to some empirical examples on some real data. So the theorem for two variables, which I already briefly mentioned by Lancaster in 1957, is that if you have two variables and they're jointly Gaussian, then it turns out that maximum correlation, which is optimizing over all function, is equal to Pearson correlation. In other words, for jointly Gaussian random variables, the optimal functions are linear. And we proved, after some work, an analogous theorem for MCPCA, which says that if you have p random vector, p-dimensional random vector, then MCPCA equals PCA for jointly Gaussian random vector variables. Okay? All right. True for every Q. In fact, this theorem says that you have a single optimizer for every Q. And this is connected to a notion called matrix majorization. Okay? But I won't go there. I would like to spend the remaining 5 minutes that I have. I understand we're going after 10:30, but remember we started a bit late. I've learned never to ask the chair how much time I have. That's one thing you learn with age. When people ask, I always say, this person's inexperienced.
Especially here, you're the chair.
Oh, I'm the chair. I'm a self-chair.
Yeah.
Self-chairing. So computation, we have made some progress, but I must say we don't have a complete solution to the computation problem. Now, the MCPC optimization is actually a non-convex optimization problem. Now, what we did was we showed that for Q equals 1, that means projection in one dimension, we can replicate the nice story for two variables, maximum correlation, which says that we can solve for the global optimizer efficiently, analogous to basically the second singular value computation of Witzenhausen. However, for general Q, we have not solved this problem completely. We've only been able to get an algorithm to converge to a local optimizer. So the results I will show empirically are under this local optimization. So potentially, if you have a better algorithm, you could get better results. Now, to connect it to data, we don't have joint distribution from data directly. What we have is empirical distribution. In other words, you collect a bunch of data, and you form an empirical joint distribution. So what we're going to do is we're going to apply MCPC to the empirical distribution. We call it sample MCPCA. Now, there are lots and lots of nonlinear dimension reduction methods. So you can think of MCPC as another nonlinear dimension reduction method because I'm applying nonlinear transformation and project it into a low dimension, right? There are many, many methods proposed. The one difference between our method and this method is that we optimize over the nonlinear transformation. This is a very important difference. We optimize over nonlinear transformation. So I would like to compare a little bit on some empirical results with these other methods. Okay, so I'll give two evaluations. One is on the UCI data set. We picked out a bunch of data sets, and we've done some experiments on MCPCA on this data set. Okay? So first, the unsupervised demonstration. So unsupervised means what? It means I look at the data, and I compare MCPCA with other nonlinear dimension reduction, and I evaluate that by looking at how much of the data variance has been explained by the projected variables. Okay? So this is a function of Q. This is a function of Q. And this for one particular of those data set. Yes?
For numeric variables or ordered, you have to limit your transformation to be monotone.
Yes, yes. So no, we do not limit to monotone. We do not limit to monotone. For the data set I'm showing here, this slide, they're categorical. The variables are categorical. So that issue doesn't come up. For real valued random variables, we can't really numerically optimize over all functions. So what we do is we limit a class of function. For example, a piecewise linear function or polynomials to up to a certain degree. So that's what we do in the numerical results. Okay? You can see here that the explained variance as a function of Q is better using MCPCA. So this is the explained variance. It's the blue for MCPCA. PCA is given by the red. So you can see that there is improvement in explained variance. And this is obtained by cross-validation analysis. So we took out half the data set. We compute PCA and MCPCA, and we evaluate on the other half. And we repeat this 10 times to get the average number here. Okay, so this is not cheating. So we're not evaluating on exactly the same data set. And for another data set, we get similar but smaller amount of gain. So what we showed is that in all the 6 data sets we have gain. These 2 data sets are the ones which the gain is most significant. The other ones are, you have a little bit gain, but not very significant. Okay? Now, we asked the question, well, what about supervised? So this is unsupervised demonstration. So we did an experiment on the data sets again. So what we did is we used the nonlinear dimension reduction method to reduce everything into one dimension, so Q equals 1. And then we compute the correlation of this feature with the phenotype. Now the phenotype is completely separate. The MCPC or other nonlinear dimension reduction method is applied only on the feature space. So what we showed is that the MCPC seems to be capturing a good correlation with the phenotype as well. So this is the highest. And the other ones are lower. And these are the confidence intervals. Okay? Yeah.
These features are, there's no relation, let's say there's no relation between them and the phenotype, and you don't see anything, you know?
Yeah, but in this data set, there are a relationship, obviously.
But when you did PCA or the XPCA,
Yes.
you don't know about the phenotype.
We don't know about the phenotype.
There's no reason for them to be optimized in the direction of it.
Exactly, but it turns out to be.
That's what I'm asking.
Sorry?
I mean, like, why would it be?
But you're hoping, I mean, any dimension reduction method, right? What are you doing? You're projecting your high dimensional feature space in the low dimension. Your hope is that it will capture some correlation with the phenotype because you're going to do supervised learning, for example, on this low dimensional space. So that's the hope. And what we're saying is that MCPC delivers on that hope, at least on this particular data set, better than other methods. And similar for another data set. So there are 4 other data sets. Again, MCPC is the best, but the gain is not as much. It's relatively small. OK, so I thought, OK, since this is the bioinformatics meeting, so I thought I better show some bioinformatics data set. So this, I must admit, we've done in the past 2 weeks, okay? Past 2 weeks, just for this meeting, But just to get some feel on sort of what kind of data set can we apply this method and see what happens. So this is exploratory. So what we did is we applied on a single cell data set. This is a 10x data set in Nature 2017. There are 68K cells and 20K total number of genes. Okay? We picked out 1,000 highly variant genes, similar to that paper. So now we have P equals 1,000 genes, and data 68K. And again, we do a cross-validation study on how much gain you get by doing MCPCA in the explained variance as a function of Q, the dimension you projected down. And here we see about a 30%, roughly 30% or so gain in the explained variance. This is without taking log transformation on the data. Once again, with log transformation, we see similar gain. So it depends on what school of thought you have. For people who like to take log transformation, we get a gain. For people who don't like to take log transformation, we also get a gain. So there's some dispute for single cell data whether or not we should take log transformation. For bulk, according to Leo's lecture, we should take log transformation. That's what he told us. But single cell, he did not say anything. So it doesn't matter. Either way, it's fine. Yes, your question.
Just to make sure we're talking about expression data, right?
Yes, these are expression data. Sorry, I didn't spend time in explaining the data. So we have single cell data set. So we have expression data on each cell, about 68,000 cells. Each expression data is a vector of 20,000 dimension, number of genes. We pick only 1,000 of those dimensions, the ones with the highest variant genes. That's what 10x paper did. Okay? Now, if we do cluster, yes?
So the MCPCA, shouldn't it be this exact same thing? It doesn't matter, right? The labeling doesn't matter. So the log transformation in principle shouldn't matter.
Yes. So yes, exactly. So let me ask you let me break down your question into 2 parts. One is that PCA matters, right? So you see the difference. Now MCPCA in principle should not matter because this is good. This guy's really understanding the talk here. Thank you. I hope you're not the only one though. Yes. MCPCA allows all nonlinear transformations, so it should absorb the log. However, because we have numerical constraint, we only allow polynomials up to degree 3. That's the class of transformation we use. And so we cannot absorb the log. So here there is some difference. Okay, good. Yes?
Data with like ordered or real data, if you allow all transformations, you can always get perfect, no? If you can sort of rearrange the values to get one with one.
No. So that's a very important point.
As long as each value is unique.
No. We cannot get perfect. And the reason is because we are allowing arbitrary transformation, let's say, in theory, but we're only allowing transformation on each feature separately. We're not allowing to take joint transformation. If you could do that, then you could get everything. However, if you can do that,
You can get to one, but
yes, but then you'll be overfitting the data for sure. So in some sense, MCPCA is a trade-off between overfitting the data and allowing some flexibility. And we chose this particular one. Maybe you want to choose a little bit more flexibility. For example, by taking pairwise transformation. OK, so I see that although I'm the chair, the real chair is actually looking at the clock right now. So I'll quickly finish. So we did some clustering analysis. And we show basically that MCPCA and PCA has pretty similar clustering on this data set, 94% of the cells. However, when we look at the clustering, what we find is that so here I'm measuring the correlation between the cells to the center of each cluster. And we find that in MCPCA, the correlation is stronger. That means that the cells seems to cluster a bit better, more central. And there's a difference between MCPCA. And if we look at the 6% cells which have different labels under MCPCA and PCA, then you see that MCPCA seems to be stronger centering versus PCA, whereas PCA seems to have a bunch of outliers here. So it seems that preliminary analysis seems to suggest that MCPCA may discover something interesting about these 6% cells. But this is when time is up, and I have to give this talk. So we stop here. All right, thank you.
In the case of bivariate variables, the maximum correlation between -1 and 1, so you can interpret it quite easily. Is it like a natural scale for the MCP?
Yes, it's natural scale because the sum of the eigenvalues is normalized.
Yep.
So therefore, there is a scale associated with the problem, right? Yes.
How sensitive is this to like variable dropout? So if you take columns out of your matrix, how much does that change the values between each pair of? So if you have like a 3x3 matrix and you lose a variable, say you have age, sex, and say cancer stage, you lost cancer stage, how does that affect the correlation between age and sex? Because presumably it's different depending on how much data you have in your matrix.
So if I lose a feature entirely across all my data points, right? Then I have a lower dimensional matrix. Then you're going to do MCPC on that matrix instead. So your question is how much perturbation I have
For the variables that still remain.
for the variables that still remains. Okay, so good. That is an interesting mathematical question. So the question here is that when you remove a column from a matrix, how much perturbation to the singular values to this matrix? So there's a whole lot of theory on this problem. And the hope is that if you have a very high dimensional, so I don't think there's a single universal answer to this because it depends on the underlying joint distribution, but perhaps one can bound the perturbation. That is an interesting question. We can talk a bit more offline.
I think we should go straight to coffee. Okay,
But Ben was just about to ask the question.
we got quick announcements. We have